Okay, so in the interest of time, let me directly go to the topic of this discussion. The title of the presentation is Electricity Generation from this acid-base chemistry. So, as you all know, this acid-base reaction is a classical chemical reaction which involves the recombination of H plus and OH minus liberating water molecules, and the reaction happens to be exothermic in nature, which means the enthalpy change of the reaction is negative. And what I'm going to talk to you today, how to interconvert that heat into electrical driving force. And there is huge industrial prospects in harvesting that energy as electrical driving force, majorly because the global annual acidic waste is almost 100 million tons of sulfuric acid, and before discharging them to water bodies, they undergo a neutralization reaction, and tremendous amount of energy is wasted in that process. And if you do it by calculation, the amount of energy wasted corresponds to this much amount of electrical driving force, which is very significant. Apart from this, at a very fundamental level, the reaction pathway is very exciting because of its positive entropy change. And you can see this reaction pathway has got a positive entropy change that in fact leads to a thermodynamic efficiency greater than 1. It is close to 1.43. Thermodynamic efficiency greater than 1 signals that when the reaction pathway proceeds in the system, that reaction pathway is able to harvest the energy from the surroundings also as electrical driving force. That is why it is higher than 1. That is why when I raise the surrounding temperature, this is surrounding temperature, that is why when I raise the surrounding temperature, the electromotive force of the device is commensurately increasing. On the other hand, if you compare it with a conventional hydrogen-oxygen fuel cell pathway, you can see an opposite trend. When I raise the surrounding temperature, the open circuit voltage is decreasing commensurately, suggesting that when the reaction pathway proceeds, a part of the energy is lost as heat to the surroundings for this particular reaction pathway. So in comparison, you can see that the neutralization reaction pathway is quite distinct and significant. It is fundamentally very exciting because it can harvest the energy from the surroundings also as electrical driving force, and technologically the reaction pathway is very, very important for interconverting that heat as electrical driving force. However, the problem is, the challenge is, this reaction pathway we are talking about is a non-redox reaction. If you look at the left-hand side and right-hand side of this reaction pathway, you can see there is no change in the oxidation state of any one of the species involved in that reaction pathway. It happens to be a non-redox reaction. And in electrochemistry, to interconvert the reaction pathway as electrical driving force, the reaction has to be a redox reaction. For example, if you take the conventional Daniel cell reaction, you can see this is a total cell reaction, and in the left-hand side zinc half cell, the reaction that is going to happen is the oxidation of zinc to zinc 2+. And you can see there is a change in the oxidation state of zinc there. And what is the consequence of that change? It will liberate electrons, and those electrons will move through the circuit providing us electricity, and the moment those electrons reaches the right hand side copper half cell, it will prompt the reduction of copper 2+ to metallic copper. You can again see there is a change in the oxidation state of the species involved, and this change in the oxidation state of the species involved in the entire reaction pathway is very, very important in interconverting the reaction energy as electrical driving force in electrochemistry. Unfortunately, that is not the case in the case of the neutralization reaction. That happens to be a non-redox reaction, even though it has got huge industrial prospects and fundamentally very exciting reaction pathway. And we have overcome this challenge by utilizing what is called a hydrogen redox, because we realized that the hydrogen redox is a pH-dependent electrochemical reaction, and for that reason, the electromotive force of the reaction, as per the next equation, has to be pH-dependent, which means when I change the pH, the electromotive force has to shift commensurately according to the next equation for this simple hydrogen redox. That is why this is the current voltage curve of the hydrogen redox reaction. That is why you can see here the current voltage curve of the hydrogen redox is shifting negatively along the potential axis when I increase the pH to alkaline. And you can see in the alkaline medium, the hydrogen redox is negative compared to the acidic pH. In electrochemistry, anything negative tends to be anode. Tends to be anode means it tends to undergo oxidation, whereas anything positive tends to accept electrons, which means tends to be the cathode. Which means this understanding offers us to overcome the challenges associated with the neutralization reaction. Because if I decouple the direct acid-alkali chemistry as shown here, and if I perform the hydrogen redox in the decoupled acid-alkali configuration as shown here, the alkaline half cell has to be negative corresponding to the acidic half cell. Which means the alkaline half cell has to be negative compared to the acidic half cell, which means the alkaline half cell should experience oxidation reaction compared to the acidic half cell that has to accept electrons. Which means the alkaline half cell will experience oxidation reaction, means the hydrogen will undergo oxidation, liberating electrons in the alkaline half cell, and those electrons will travel through the circuit providing us electricity, and the moment those electrons reaches the right hand side half cell, which is positive, it has to accept electrons, and the species available there to accept electron is simply the protons. And when they accept electrons, the reaction that is going to happen is simply hydrogen evolution, which means if you look at the first reaction, it involves the consumption of hydrogen, and second reaction, it involves the evolution of hydrogen. Then there is no net consumption of hydrogen, and the question is, then what is providing you electricity? There is the difference between the two reactions, that is simply the neutralization reaction. So by utilizing this hydrogen redox, we can actually harvest this neutralization reaction pathway directly as electrical driving force. And this is the performance metrics of the device. And this is how electrochemists usually test the performance of any device. You draw different amounts of current and you monitor the evolution of cell voltage E as a function of the current drawn. And you can see the performance metrics are reasonable and decent, not very bad. And this third plot is very important, that is the in situ electrochemical mass spectrometry during the device operation. And you can see when the device is on, when the device is in the operating mode, and when I perform the in situ electrochemical mass spectrometry, these are the signals for hydrogen. You can see in the anodic half cell, the green trace, the pressure of hydrogen decreases, suggesting that hydrogen is consumed, whereas in the cathodic half cell, the pressure of hydrogen commensurately increases, suggesting it is evolved. This says that there is no net consumption of hydrogen, and this reaction is actually propelling the operation of this neutralization pathway. And to unambiguously verify that the neutralization is involved in electricity generation, we have drawn a constant current from the device till the electromotive force drops to zero, and commensurately we have measured the pH in both the half cell, and you can see they converge towards a neutral pH. And when no current is drawn from the device, you can see the changes in pH in both the half cells are almost negligible, suggesting these changes that you are observing when current is drawn is due to this reaction that is happening electrochemically, not chemically. I have a video demonstration and I believe it will not work. I think it works. You can see when I draw, the most important thing is there is no net consumption of hydrogen, which means whatever the hydrogen that is evolved in the cathodic half cell, whatever the hydrogen that is consumed in the anodic half cell has to be evolved in the cathodic half cell. So I connected the cathodic half cell to this particular tank, and you will see that there will be bubbling of hydrogen in the cathodic half cell. Whatever is consumed, that is evolved. If that is true, I can replace this tank and I can connect a hydrogen oxygen fuel cell there, and it can draw that hydrogen and power another device. That is what is shown in the next device. I simply replace the tank by another H2O2 fuel cell, and whatever the hydrogen that is evolved as a result of that neutralization reaction will be consumed by that H2O2 fuel cell to power the second load. You can see it is beautifully powered, which means the concept is actually possible. This electrochemical neutralization, according to me, has got a huge potential in electrochemical process modulation. It can be utilized for various applications, and it actually provides various possibilities and opportunities. And we have explored several of them in our laboratory, and first one of them is the possibility of desalting saline water. Okay, the desalination of saline water is very important to produce water for drinking purposes and agricultural purposes, and to effect that possible with the help of electrochemical neutralization, we have actually designed a 3-compartment cell, and the middle compartment house the water for desalination. And you can see the top half cell reaction, the reaction that is happening in the top half cell is as shown here. And it involves the consumption of hydrogen and also hydroxyl species, which means when this reaction proceeds, there is actually a kind of charge imbalance in the top half cell with respect to the anions. So to mitigate that charge imbalance, Cl- from the middle saline compartment should move towards the top half cell through the anion exchange membrane AEM. Commensurately, what is happening in the bottom half cell? That is shown here. That is the hydrogen evolution reaction, which involves the consumption of cations. And again, there is a charge imbalance in the bottom half cell with respect to the cations. To mitigate that charge imbalance, Na+ from the middle saline compartment will move through the cation exchange membrane CEM to the bottom half cell. So the net result of the electricity generation by utilizing this electrochemical neutralization is a net desalination that is happening in the middle saline compartment. So we have monitored the desalination flux by various methods when no current is drawn from the device. The desalination flux is found to be very negligible, and when a current is drawn, you can see there is a drastic decrease in the concentration of NaCl in the middle saline compartment. And the desalination flux, when I draw a current, is found to be 200 times higher than what is observed when no current is drawn, which means that the electricity production actually provides an alternative route for desalination by the concerted motion of Na+ and Cl- ions towards the respective, the half cell. And we have also measured the charge balance, the correspondence between the charge passed, NaCl removed and H+OH- consumed. And we found that there is actually a very good correspondence between all these three parameters, suggesting the occurrence of negligible parasitic chemistry during the desalination process. We also computed the desalination efficiency by what is called, by designing two types of devices, one with the middle saline compartment and one without that. And the difference should correspond to the energy invested for removing salt from saline water. And that is close to what is reported in the literature for the best RO process. And also we could utilize this approach for removing salt from real seawater collected from the Arabian Sea, and therefore this electrochemical neutralization provides a lot of opportunities. And the second application we have explored is the development of an alcohol reforming fuel cell, which is quite straightforward if you look at this fundamental reaction pathway governing the energy of neutralization. Remember one thing, that there is no net consumption of hydrogen, okay? And if I replace the hydrogen that is bubbled into the anodic half cell by a hydrogen carrying molecule like methanol, the reaction will be transformed to something like this. And you can see, if you look at this reaction very carefully, on the right hand side you have hydrogen evolution at the expense of the consumption of methanol alcohol. Or I would say this is converting methanol to hydrogen during electricity production. And if you compare this reaction pathway with the conventional, direct methanol fuel cell, you can see the difference. In the direct methanol fuel cell, you cannot see the additional component of hydrogen evolution that you see here. So clearly, the reaction pathway based on the energy of neutralization can reform alcohols to hydrogen during electricity production, and that is possible only because of this energy of neutralization. And remember one thing, that alcohol reformation to hydrogen usually requires very high temperature and pressure, and by utilizing this energy of neutralization approach, you can actually interconvert alcohols to hydrogen at room temperature and pressure, and that too during electricity production. And we could reform a range of alcohols including methanol, ethanol, and various aliphatic alcohols, aromatic alcohols, diols, triols, and including naturally occurring sugars like glucose to hydrogen during electricity production. And the most important thing is this device actually produces hydrogen, the alcohol reforming fuel cell, which means I can connect it to a hydrogen oxygen fuel cell as its fuel reservoir. Which means when this device is operating, I can actually power a hydrogen oxygen fuel cell commensurately. And if that is true, their time of operation should coincide, because if this device stops functioning, automatically this device should also stop functioning, which means their time of operation should coincide, and that is what you are seeing here. I have a video demonstration. I hope it will work. Okay, I'm sorry about the music. It It's anyway, I cannot do anything now. So this is the alcohol reforming fuel cell which we have developed, whatever here. So, and this one, and you can see a lot of hydrogen evolution that is happening during the alcohol reformation. And you can see a lot of hydrogen that is evolved. And if that is pure hydrogen, you have to bear with me with this music also. If that is pure hydrogen, I can connect it to a hydrogen-oxygen fuel cell, and that should be able to power that device directly without any fuel purifier. So I can reform alcohols to hydrogen during electricity production, and the same device is going to power a hydrogen-oxygen fuel cell simultaneously. And you will see that everything in one screen now, you can see everything is powered by the same alcohol reforming fuel cell. So this pathway is very powerful and quite unexplored in the domain of electrochemistry. And the third possibility we have explored is the possibility of fuel purification. Again, that is quite straightforward if you look at the reaction pathway. You can see hydrogen is consumed in the anodic half cell and it is evolved in the cathodic half cell. Okay? And remember one thing, that hydrogen is the electroactive segment for this device. Without hydrogen, this device cannot function. That is what is shown here in this particular plot. When there is no hydrogen, as shown by the red trace, the cell voltage abruptly drops to 0. And when there is hydrogen, you can see the device can be run for several hours, which means hydrogen is the electroactive segment. But the most important thing is there is no net consumption of hydrogen. If 10 molecules of hydrogen are consumed, there has to be 10 molecules of hydrogen evolution in the cathodic half cell. There has to be a one-to-one correspondence between the hydrogen consumption and evolution. And this understanding offers opportunities for fuel purification. Because, for example, if I replace this hydrogen stream by an impure stream of hydrogen, H2 plus X, where X is the impurity, it can be CO2, it can be nitrogen, etc., etc. Only the hydrogen undergoes oxidation, and corresponding to that degree of oxidation, there has to be hydrogen evolution in the cathodic half cell. And you can see you get very pure hydrogen at the expense of impure streams of hydrogen, that too during electricity production. And remember, hydrogen fuel purification, the state-of-the-art methodology employed for hydrogen fuel purification, like membrane gas separation, pressure swing adsorption, cryogenic distillation, they all require extreme temperatures and pressures. And here it happens at room temperature and pressure, that too during electricity production. We could purify hydrogen from binary mixtures, and we could also, as you can see, in situ electrochemical mass spectrometry shows that in the anodic half cell you have all the impurities, whereas in the cathodic half cell you have only pure hydrogen. The same thing is observed even in the case of H2CO, H2H2S mixture. You can see in the anodic half cell you have all the components, in the cathodic half cell you have only very pure hydrogen. We could also purify hydrogen from a quaternary mixture of impurities. You can see in the anodic half cell you have all the 4 components of the impurity, including hydrogen, whereas in the cathodic half cell you have only very pure hydrogen, and the energy efficiency is computed and the purity is also calculated, and it is in par with the rest of the methods, but there is an additional component of electricity output in our method because of the acid-base neutralization reaction. So this methodology is very powerful. I will skip this video, and the last one which we have recently explored is a heavy hydrogen generator based on the same concept. The methodology is very simple. In the first case, I replace the hydrogen by methanol. In the second case, I replace the hydrogen by impure streams of hydrogen. In this case, I replace the H plus OH minus gradients into D plus OD minus gradients. And you can see the reaction will be transformed to something like this. If you look at the reaction pathway, it's clear that you generate heavy hydrogen at the expense of light hydrogen. You can clearly see that. Which means you interconvert light hydrogen to heavy hydrogen by utilizing this D plus OD minus gradients instead of H plus OH minus gradients. And heavy hydrogen is produced at the expense of light hydrogen. Heavy hydrogen production is extremely significant in industrial sectors like nuclear, pharmaceutical, chemical, and various sectors. It finds a lot of application, and the state-of-the-art methods for producing heavy hydrogen is heavy water electrolysis. You have to invest a lot of energy. And here it is produced during electricity production. And in situ electrochemical mass spectrometry clearly shows that in the H plus OH minus system, hydrogen is consumed in the anodic half cell, whereas hydrogen is evolved in the cathodic half cell. If I change the H plus OH minus gradients into D plus OD minus gradients. You can see hydrogen is consumed in the anodic half cell, whereas heavy hydrogen is evolved in the cathodic half cell. So it clearly validates that heavy hydrogen can be produced at the expense of light hydrogen. And this video demonstrates this heavy hydrogen generator. This is the device made by students. This is the heavy hydrogen generator, and the power of this device is given to this small device which is kept here, and the cathodic outlet where heavy hydrogen is evolved will be collected here, and it is connected to a heavy hydrogen oxygen fuel cell that is kept on the right side. And this is just they are going to show you an overview, and so this is the device made by my students, and several of them are stacked together to amplify the voltage output. And this device is connected to, the power of this device is given to this small lamp, which is also made by my students. And during that process, there has to be a lot of generation of heavy hydrogen in this particular one. In this particular switch will be collected here. When I open this particular knob, you will see that there will be a collection of lot of that gases in the other side of the storage tank. So this methodology shows that this energy of neutralization actually has got a lot of opportunities in electrochemical process modulation. So when they open the knob, you will see a lot of bubbling in the storage tank. Whatever the gas that is collected now will be evolving into this storage tank, and if I open this knob now, whatever the heavy hydrogen that is collected will be gone into this, will be supplied to this fuel cell which is kept here, and that will be able to power this particular load that is connected to this fuel cell once I open that. You can see that it is being powered. So to conclude my talk, this energy of neutralization is actually a powerful reaction pathway, even though it's very classical and century-old chemistry. It can be used for various electrochemical process modulation. It can be, so I have shown you the possibility of fuel purification, desalination of saline water, spontaneous heavy hydrogen evolution, and alcohol reforming fuel cell. It has got various other possibilities as well as shown in this slide. And finally, before concluding, it is also possible to design an electrochemical stub. And this is the device that is made out of the neutralization, and the hydrogen, the power of this device is given to this table fan, and the hydrogen that is collected, that is evolved, will be collected here, and that is connected to a stove here, and you can use it for cooking your omelette during, say, when you are powering your electronic devices. That flame you cannot see, so I have a trick to show you the flame. And that's it, and it's very powerful approach, and thank you very much for listening to my presentation.
Any questions?
For saline water, how much water can generate?
Sorry?
How much liter of water can generate saline water to pure water for this?
We have tried from 15 ml to 100 ml. We have not tried beyond that level because you are talking about the desalination of saline water, right? Yeah. So we have tried in the ml level, from starting from 15 ml to 100 ml level. Beyond that level, we have not tried.
Thank you.
Any more questions on the floor? So thank you, Professor Muhammad Musthafa, for your energetic and engaging session. So I'd like to call upon our Assistant Professor, Dr. Ravi Kumar, to felicitate Dr. Mr. Muhammad Musthafa.
Thank you very much. I hope you have all enjoyed the exciting talks from the academics and industry. So I'm just going to give you only a brief overview of what we are doing at Atria University. So Atria University has just begun its research chapter in the R&D, and also we give a service for some of the industry as well. So I would like to just give some research activities that we do in the energy science department. So I'll give a brief introduction about what we do, battery research, and also some of the green hydrogen research that we are working in this department. So these are some of the key areas that actually we are planning to work on: lithium-ion batteries and different metal-ion batteries, basically looking into the solid-state electrolytes and new materials and safety diagnostics and battery management system, etc. And on the hydrogen side, so of course there is a lot of potential interest for green hydrogen and fuel cell or the CO2 to fuel, etc. So the lithium-ion batteries have revolutionized the e-mobility industries and widens the opportunity for research and developments. So you can do a lot of things, as we scale up these for various applications. For example, you can look for new materials and also the state of the health and give a diagnostics and so many things. For example, this is just a very fundamental level of understanding a battery, where you do a full charge discharge and also at the individual electrode how the interface, for example, the lithiation or delithiation, and whether it's a plating with respect to the safety aspect of the battery. Okay, so when the Atria University has started its battery research lab, the faculty members here have begin with the research, looking at the what are the available research resources. I think they just started looking at some of the material sides. One of the interesting project is on the deriving bio-based carbon for conducting purposes. For example, the lithium-ion batteries have a cathode materials which require some of the conducting substrate like carbon. So the acetylene black is widely used as a conducting carbon, and because of its expensive nature, so people have demonstrated or looking at the different aspects of a carbon which can be derived from various sources. I think they have used this terpene rich orange peel as a carbon source, and they have looked into various aspects of the battery materials, and these are some of the results. I think I'm not going to go detail. Another interesting aspect, the lithium-ion batteries, it's a well-established manufacturing process of the anode material and cathode material. So we have a current collector. For example, here you can look at the copper is used as a current collector for a battery anode material. So of course, we now have a very good materials science established, where we can get a graphene foil or a graphite foil. So instead of using a copper, we can directly use graphite as a anode material, since it is flexible, mechanically stable, and good electrical conductivity, etc. For example, if you look at the picture on the left side here, the lithiated graphite. So in the battery, when you do a large scale battery within the cell, you can see a lot of problems, mainly because of the heat management or things like that. So there you can look at here in the second picture. So there is a burning of the half of the cathode material, the anode material. So once that is burned, it cannot be reused again, because it has the entire battery has to be replaced. So if I use, for example, this graphite foil, even a top layer burns, because of the underneath layers are still available for the use of a battery material. So this is just an assumption, but a lot of research is required to prove this kind of assumptions and then bring it to the realistic systems. So this graphite foil, for example, you can look at this layered structure, and the intercalation or deintercalation can happen as usual in the other battery materials, like the graphite powder that is coated on the copper substrate. For example, if you can look at the data on the right side there. So the right one is the flexible graphite directly used without any a current collector. So you can still see a good intercalation and deintercalation processes happens, which compares to the commercial graphite powder which is on the copper plate. So, and also the transport is the ion diffusion is quite different from the graphite powder compared to the graphite foil, because of their planar structure, and also the porosity is play a wide role. So we have just began this material to look into its fundamental. So these are some of the preliminary data that we have got, and we are still looking into understanding the entire mechanism of this process. So also, if you look at the cyclic voltammogram of a full cell, which shows the reversible behavior for the intercalation and deintercalation. But if you look at the charge-discharge curve, it shows a very good voltage gap between the charge and discharge. But if you compare to the actual the graphite or a LFP cathode, you can see it's only one discharge plate or charge plate, but there you could see a two. So I think it's we don't know the exact reason behind that. Still we are understanding the mechanism behind it. So I think that will give us a development of a new material for the a lithium-ion battery, which comes for a safer side. So, and also we work on sodium-ion batteries. So in this case, we're trying to use anode material, the transition metal oxide. For example, tungsten dioxide is used as a battery anode for the lithium or sodium, so which is a good conductor and also a reversible capacity. Here you can see we have just used the simple Prussian blue analog as a sodium nickel hexacyanoferrate, so which gives a good reversible capacity and also the cycle number. So these are all some of the research initiatives that we have taken to establish the research activities in Atria University, which can take forward for us to develop or establish the energy center for them. So on the hydrogen side, so we have also started working on the alkaline water electrolysis. The proton exchange membrane electrolyzers are already established well and in the market. So because of the expensive catalyst used there like platinum, iridium, I think the alkaline anion exchange membrane water electrolyzer still can compete with the PEM in terms of performance and then the lifetime. So here we have a strategy where we can directly use those porous transport electrodes instead of using any nanometric catalyst with binders and ionomers. So because these allow us to fabricate the electrolyzer in a simple, and also the balance of plant is a simplification process. Here are some of the preliminary which can shows that these direct use of porous transport electrodes in alkaline electrolyzer can be used and made into realization, where the full cell electrolysis system also with a single cell has been set up and then studied. So I think we can see some performance which gives a good current density at a very high efficiency and also the energy consumption for the hydrogen generation. And another concept where the water, ultra pure water, is used in the electrolysis of water to hydrogen. So and it adds another cost for the hydrogen which is generated. So this concept where we can actually use hydrogen from air. So since we have a humidity present in the air, so we have designed just the open anode structure and also the proton exchange membrane or the ion conducting membrane, which is hygroscopic in nature, so which can absorb the atmospheric humidity and utilize in the same device. It converts the water into hydrogen and oxygen, and it can be the same device can be also made into a reversible fuel cell, where the same device can act as a fuel cell which converts the hydrogen whenever required. So we have got some small grant to scale up this activity from a IISER foundation set up by the IIT Palakkad. I think with that I'll thank you, and I thank for Atria University for providing all the research facilities, and IIT Palakkad Foundation for the small research grant, and IISER Pune for some of the collaborative research. And thank you for your attention.
Thank you, Dr. Ravi Kumar, for showcasing incredible research being conducted in AU COE battery team. Now I'd like to call upon Dr. Shanthan Acharya, Associate Professor at Atria University, to felicitate Dr. Ravi Kumar.